Make sure to like and subscribe right now. Yes, do it.
Hello guys, this is Rick from Mathics, and today we're going to be doing the number 11 from the AIME 1 of 2022. Now this number 11 is pretty surprising, because even though it's a number 11 geometry problem, the concepts involved and the level of creativity you need to solve this problem are actually astoundingly easy. On the real test, I actually solved this number 11 before I solved the number 3, which shows how the techniques for this problem are pretty standard when compared to other AIME problems. So without further ado, let's just get into this problem. Let ABCD be a parallelogram with angle BAD less than 90 degrees. A circle tangent to the sides DA, AB, and BC intersects diagonal AC at points P and Q, with AP less than AQ as shown. Suppose AP equals 3, PQ equals 9, and QC equals 16, then the area of ABCD can be expressed in the form of m root n, where m and n are positive integers, and n is not divisible by the square of any prime. Find m plus n. So, like any geometry problem, the first step is to create a larger version of the diagram, and then label the information we know. So here's my enlarged version of the diagram, and I'm going to put down information that I know. First, I know that the length of AP is 3, and I know that the length of PQ is 9, and then I know that the length of QC is 16. And this is actually good enough to start us off with. The first thing that should stick out to you is we have lines intersecting a circle. So we have chords. So that should make you think power of point. What power of point identities can we use? Well, we can use the identity of power of point stating that AP times AQ is equal to the tangent squared. So, taking that, we get that let's call this AT. We get that AT squared is equal to 3 times 3 plus 9, or 12. Which gives us that the length for AT and any other tangent points from A to the circle is simply just 6. So we can label AT as 6 here, and we know that this length till this point, I'll call this one, what letters have we not used? R. These both have a length of 6. Second off, we just used power of point here, but we can pretty much do the same thing with point C and the same chord PQ. Labeling this point as S, we can use the same power point identity to state that CS squared is equal to CQ times CP, which is 16 times 16 plus 9, or 16 times 25. Just simplifying this down, we get that CS is equal to 20. So now we have a pretty good amount of side lengths actually. We turned our 3 side lengths and we tagged them on to create a bunch more. And by a bunch I mean like 3 more. But that's still pretty useful. Next, what are we still stuck not knowing? Well, we don't know the length of BR. We don't know the length of BS. We also don't know the length of CD. So I feel now would be a useful time to use a variable so that we can represent a almost all the lengths in terms of a common expression. So let's say that BS is x. By the property that tangents to the same circle from the same point have to have equal lengths, we know that BS is equal to BR. So if BS is x, BR is also x as well. Furthermore, now we can actually relate this to opposite sides of the parallelogram. Since it's a parallelogram, we know that AB and CD must have the same lengths. So since we have AB has a length of 6 plus x, CD will also have a length of 6 plus x. Furthermore, using that same property, since we know that this is a parallelogram, opposite sides are equal, we know that BC has a length of x plus 20, so AD must also have a length of x plus 20. We already have that AT is 6, so TD would be x plus 20 minus 6, or x plus 14. So making progress. So this is actually pretty good. We have pretty much every side of the triangle in terms of variables, which is actually pretty good progress. But we still need to figure out the area. Now remember the deal with the parallelograms. Parallelograms, you're going to have to multiply the base times the perpendicular height. So we can't just take this base and multiply by this length, obviously. Of course, if you're on AIME, you know that for sure. We're going to have to take the perpendicular length. So it would be helpful to probably draw an altitude from C intersecting to AD. So I'm going to quickly draw that. And I'm going to extend out AD to meet it. And you know what? Let's just label this point as H. So, in order to do anything with this, it would be helpful to know what the length of DH was. But that's actually really easy to figure out, as we know that BS and AT are parallel with one another, and that this little symmetric distance from A to its corresponding H is just 6 minus x. So by symmetry, since the distance from the intersection point of the perpendicular from B to AD is 6 minus h from A, we can say that CH is 6 minus x from D. As such. And now look at it. We have the entire length of A to H, because the 6, x plus 14, 6 minus x, the plus x and minus x will actually cancel. So we're actually in great shape there. We get the entire base is, in fact, 26. So we have our total length of AH to be equal to 26, which is great. Because now that we know that AH is 26, and we already know what AC was, as its line segmented parts were given in the problem, and we drew a perpendicular distance, we can use one of the oldest tricks in competition math and in geometry itself. We can use Pythagorean Theorem. So I'm just going to write down what the length of AC is. AC is just the sum of AP, PQ, and QC, which will give us a total length of 28. So yeah, so we have the length of AC, we have the length of AH, so we can take the length of HC by simple Pythagorean theorem. AC, 28 squared, minus AH squared, 26 squared, is equal to CH squared, or HC squared, whatever, it doesn't make a difference. So this is like a little not pretty, but you can just bash it out. Or you can try to be a little sneaky with your computation, use difference of squares. 28 squared minus 26 squared is just 28 minus 26, which is 2, times 28 plus 26, 54. So we get that HC squared is 108. So then HC is equal to 6 root 3 as such. And just like that, we got the length of HC. So now all that's left to do is solve for x, so we get the official base, and then multiply that. And then we're going to get our area. So this HC we should underline, because this is important information. Now, as to solve for x, notice that we didn't only create right triangle HCA, but we also created another right triangle, DHC. And now we know the length of HC, 6 root 3, as such. But since it's a right triangle in which we have pretty much just one variable, we can actually use Pythagorean Theorem again and then solve for the value of x that works. So we basically can set up the relationship dh squared plus hc squared is equal to cd squared. So I'm going to set that once again just to the left of already written lines. We get dh squared, which is 6 minus x whole squared, plus 6 root 3 squared, which we've already computed here to be 108, is equal to 6 plus x squared. So we have one equation, one variable, perfect, we can solve for x. Now here's the thing, I can actually tell you what expression we're going to get to solve for x without even expanding this. The thing is, the 6 squared terms and the x squared terms will cancel from both sides. So essentially this problem becomes, this like the expressions after canceling it will come down to negative 12x plus 108 equals to 12x, or 108 is equal to 24x. Just using some quick simplification, we get x is equal to 9 by 2. So now we have the length of x to be 9 by 2. So if we add that to in any of these equations, we're pretty much going to get that the side length of BC, x plus 20, is now 9 by 2 plus 20, or the total length of BC is 9 by 2 plus 20. Quick maths just tells us 49 by 2. So now we have the base of our parallelogram and we have the height of our parallelogram. So in order to get the area, we'll just multiply these two values. So BC times HC becomes 49 by 2 by times 6 root 3 the 6 by 2 will cancel out, and it'll be 3 root 3 times 49, which will give us 147 root 3. So this is our answer. This is the area of the parallelogram. But the problem doesn't want radicals because it's AIME. It only wants integer answers. So it wants what m plus n is. Since we got our m to be 147 and we got our n to be 3, m plus n is just 147 plus 3, which is just 150, which is the answer for this problem. So as you can see, this problem was pretty easy. I mean, this is the number 11, but what did we use here? We used PowerPoint, which is pretty, like, it wasn't like it was hiding PowerPoint. PowerPoint was pretty visible just by looking at this problem from a first glance. We just set up variables for unknown values, pretty standard technique. We drew a perpendicular projection, which is what you should do with these kinds of problems. And then we just used Pythagorean Theorem and we solved for the values and took the area. So even though this is an AIME number 11, all the techniques here were pretty standard and you really didn't have to be too creative with this usage. Yeah, as I said, on the real AIME exam, I actually skipped over Like, I saw this problem, this number 11 geometry before getting back to my number 3 geometry, because I just thought that was a little bit more tricky. Which always shows, like, you don't always have to follow the order that these tests present the problems to you in. Breaking the order can allow you to take out some of the later problems, which in some cases are significantly easier, as shown with this problem. So without further ado, I hope you learned something, and please tune in next time for maybe the next math or physics problem that we'll cover.